Hello. Hi, I'm Markus, and I'm the host of the Neuro-symbolic discussion table. And first of all, I want to thank the organizers of the Wolverine workshop for inviting me. That's very nice, and look forward to the discussions later. In this overview talk, I want to briefly cover the recent progress on automated reasoning with the help of neural networks and other success stories in neurosymbolic reasoning. And in the end, I want to try to convince you why we should also take a look at natural language. About me, I work at Google in the End2Formal team, and we're a small research team consisting of Christian Szegedy, Yuhai Wu, Charles Stans, and me. And our mission overall is to build an automatic mathematician. And for us, this consists of these two tracks. One is theorem proving in a formal setting, and the other is natural language. I'll come to that later. The dream of machines that can reason is pretty old. It's certainly not starting only with our project. It has been formulated in different ways by many of the early heroes of computer science. And only fairly recently, maybe since the 2000s, for example, by Stefan Schultz and Joseph Urban, machine learning has been actively used for automated reasoning. The first attempts to use machine learning in this field actually happened way before deep learning. And so many of the early approaches used fast machine learning techniques and less powerful machine learning techniques. And they replaced, for example, individual heuristics in existing reasoning algorithms. For example, to recommend related theorems. Recently, this area picked up a lot, and many new researchers streaming in, trying to apply deep learning in ways to that. And I'm going to cover a couple of those ideas today. It started mostly with the premise selection problem. The premise selection problem is, or in particular, it started with the premise selection problem in first-order theorem provers. And the premise selection problem there is that we have to, like when we want to, for example, run a proof step or so, we want to find the lemmas or axioms or definitions that are most relevant and kind of plug them in this proof step. That's an incredibly important step for the performance of fully automatic reasoning systems, as there are often like lots of potentially related lemmas or premises. In particular, when we run these systems in a setting where there's not a human guiding them, but when these systems are supposed to prove things fully automatically, they have to find out themselves what they have to use, and there are kind of there's lots of math available they could use. They have to find out which. Deep math in 2016, 2017, and came along and applied a deep learning approach to the premise selection problem. This means that they first map these statements, these formal statements, into an embedding space. This means they use a neural network to read in the text of the proof goal, for example, and map that to a vector of real numbers. And they do this both for the current proof goal and for each potential premise. And then they compare the goal embedding and the premise embedding in a pairwise manner with another small neural network, and that neural network is supposed to output a high number when it's potentially relevant premise, and otherwise a low number. And they've shown that they can improve first-order theorem provers that way. And that was a nice breakthrough result, and that kicked off a lot of different works, which I would summarize as neural theorem provers. There are various systems. There's our Hollis system, but there's also tic-tac-toe, gamepad, cogem, GPTF, int prover, and tactic zero, and probably I'm forgetting a couple of them. These systems typically build on top of existing proof assistants such as Lean, Cog, Isabelle, or Light, or so on. And the basic idea is that these in these neural theorem provers, we replace the human that is typically using these systems by a neural network. And this means that the neural network suggests proof steps, and the proof assistants execute them and check when the proof is complete. And in this way, we get a strong combination of proof automation and correctness guarantees. The picture here in this slide shows a search tree that was produced by our HOLIS system. Just to explain it a little, these boxes here are states that or statements that the system is supposed to prove. So the topmost one is the theorem statement it set out to prove, and then and these oval nodes are proof steps it tries to apply to them, and they are colored by whether they are successful, then they're green, and or if they're in the yellow, they're a timeout, or they're red, they just failed, couldn't be applied, or led to some error state. And so you can kind of try to use these neural networks to expand the search tree and kind of get to the goal, which is to prove all the statements that you started to prove. These neural theorem provers can either be trained on proofs that humans wrote, or alternatively, they can be trained in a reinforcement learning loop. And this can result in a very strong performance compared to previous approaches. For example, our HOLIS system proved around 70% of the theorems formalized in whole light completely automatically, whereas previous systems on very similar benchmarks maybe reached only around 40% optimistically. So we believe this is a major step towards the automation of mathematics and reasoning. Here's an example proof produced by our system. The statement that's supposed to be proven here is about a convex set S and an affine set T. And it says that the closure of the intersection is equal to the closure of the convex set intersected with the affine set. And unless their relative interior is empty. So that's the thing before the implication. The point is that this is a reasonably complicated statement. I would have to kind of look up what these things mean and kind of figure out why that's true. And in fact, it seems to be a non-trivial statement. And the human that originally formulated that and proved that used around 40 proof steps. And that's a medium long proof. Our system found a proof that's just 2 steps long. And so the way this would be processed is that we first show the original theorem statement to the neural network and ask it to predict which tactic comes next. And the first thing it predicted was the simplification tactic with a list of potential, or with a list of premises. These are in this case lemmas and definitions. I think in this case only lemmas, no definitions, that it wants to use in combination with the simplification tactic. And the author of the original proof, John Harrison, confirmed that the proof idea used here is actually a different one than he used, and it's an elegant way to simplify this whole thing. So this is kind of this shows that I think there is quite some promise in this kind of system, that they can already sometimes be helpful. Now I want to shortcut to some other success stories. Over the last couple of years, a new neural architecture, the transformer neural networks, have risen and solved now a bunch of previously disconnected problems. They were at first they were successful in language, is what they were originally designed for, but it turns out they can also process images and maybe even videos and things like that. So they are incredibly flexible. And it turns out they can also be used to solve mathematical problems. Probably the first significant work on that front was by Guillaume Lempel and Charton, who've shown that we can predict the integral of formulas and predict the integral of formulas directly and compete with tools that were designed for that, like Mathematica. It's not that they are necessarily always better, but they are definitely capable of doing or definitely helpful in this case, and they can sometimes outcompete other tools that work with symbolic, that work in a purely symbolic way. We've also contributed to that list. We published a work that showed that we can predict, for example, missing assumptions of theorems. So if you enter a kind of incomplete statement and say, oh, under which circumstances is this true, it can give you an assumption that that makes it true. And it's a non-trivial one, but you could always enter false, which is nonsensical or a vacuous statement, then, but it actually gives you nice assumptions. Like here in this case, it says y1 and y2 should be non-zero. Stanislas Polu and Ilya Sutskever have shown that you can also directly use these transformer networks in proof assistance, so feeding in back into the theorem proving track. And Christopher Hahn and some collaborators have shown that we can even directly solve some problems in verification, like predicting the traces that satisfy LTL formulas, and again, sometimes compete with tools that were designed for that and that rely, for example, on SAT solvers. It's a pretty impressive demonstration. I think recently Christopher Hahn and Frederick Schmidt then went further and even shown that you can, to some extent, even solve the LTL synthesis problem with that, which is an even harder problem. So it seems that we are finally at this point that we have neural networks that can solve interesting symbolic problems. Now, zooming out a little, there is much more work on reasoning. Reasoning is becoming a really interesting problem in general machine learning. There are many works in vision. I just picked out one and that kind of that talk about reasoning, like how objects that in a video or a picture may interact, but also in natural language where there is kind of multi-hop reasoning in the form of, say, natural language. But in natural language, it also starts to become a topic to kind of mix in mathematics. For example, in the drop benchmark, there are many questions of the form that can test arithmetic abilities of these language models, given the text question, like this one, like in this year, I don't know, like that year, his untitled painting of a halo black-headed man with a bright skeletal bottle and so on kind of sold for this much, and that was higher than an estimate given earlier. What is the difference? So I mean, so it's obviously still kind of relatively simple questions here, and they seem to, and these language models also seem to struggle sometimes with more complicated questions. But it's an interesting development to be aware of. Now I want to briefly try to convince you that natural language is extremely important for the going forward in this field. It's quite impressive what these neural networks can already do on these formal reasoning benchmarks. But I think that in order to make quick progress in this field, we definitely need natural language. First of all, almost all of our knowledge about mathematics and logics and other technical subjects is only available in the form of natural language. While we have papers and books that use also formal or more or less formal language, these formulas used in most papers and technical descriptions only make sense if you consider them in the context of the natural language that is around them. Like that. They're not kind of, it's not a fully formalized thing. And so I think we need systems that can tap into this pool of knowledge. Because otherwise we will have to formalize lots of these things ourselves in order to teach these systems. And that is a very slow and very expensive path. Also, even if we were able to build an extremely intelligent, say, theorem prover, it might not help us as much as we like to, because the things that it proves may not be really understandable to us, and we wouldn't have a chance to judge whether that's interesting or not, unless it can also explain that and tie that back into the theories that we care about. And so I think, yeah, a system that can explain itself in natural language would be extremely important here. On that path, we see that there's now a big challenge that already has some first attempts of solving, but is still wide open. And that is that we find ways how to align natural language and formal language, by which we mean that these, at the very least, we would like to have like guesses as to which natural language statements correspond to which formal language statements. And because that would maybe help to bootstrap systems to kind of read both and use the one for the other. So that would be, that's essentially a wide open problem right now. There are some first promising approaches. There are some approaches in machine learning, like using auto-formalization, auto-translation, that could be maybe used for this kind of a task. And we have tried it, and there are some first signs that this could work, but it's a pretty tricky topic. So, okay, with that, I'm at the end of my presentation. I was able to get people interested in this vision of neurosymbolic approaches. I would love to discuss this and other things I may have missed at the discussion table or elsewhere. Thanks for the attention.